Okay, picture this. It's Friday. You just got home from work, 2 hours late due to unscheduled overtime because your company decided that today, that thing that wasn't a big deal on Tuesday, well, today they reversed course and decided that it was actually super urgently needed last week or so. So you got it done. Thank you for your service. But now you're exhausted, you're hungry, your wallet is empty, and payday is still a week away. But you have no food in the house except some ramen noodles and maybe half a bag of chips, which is like 6 chips in this economy. But then you spot it. Behind the 14-month-old sriracha bottle and the fruit salad that you thought you'd buy to start eating healthy, but that never happened, is that forgotten leftovers from your feast at the burrito barn last Saturday? You gingerly lift the styrofoam container out of the fridge with bated breath. Feels heavy. There's at least one full meal left in here. Your eyes start to glimmer like you're Captain Jack Sparrow capturing the Black Pearl. So you open the container and you inspect your loot. You're greeted with an amorphous mess of puke-colored sauces, watery paste that probably used to be beans, shredded bits of soggy tortilla, and darker chunks that might possibly be meat, but you're not completely sure. You don't remember exactly what you ordered, and the forensic investigation of your takeout in its current state would be near impossible. It smells off, but it's not to the point of being gag-inducing, and there's no visible mold. Now you're presented with a dilemma. Do you assume that your food is safe and edible? Or that it's too far gone, and so your weekend will sadly begin with undergraduate-grade ramen noodles? Your evaluation of the question, "Is my food spoiled?" This is a classic and very consequential example of the trade-off between Type 1 and Type 2 errors. When we're testing a prediction with a binary outcome, for example, something that is or is not, true or false, yes or no, positive or negative, there are generally 4 possible outcomes. I can predict a positive result while the actual result is positive. This is called a true positive. And I can predict a negative result while the actual result is also negative. This is called a true negative. And if my prediction accuracy were perfect, the story would end here. However, with imperfect information and imperfect diagnostic tools, for example, reality, it could also be the case that I can predict a positive result while the actual result is negative. This is a type 1 error or a false positive. It indicates a mistaken rejection of the null hypothesis. Alternatively, I can predict a negative result when the actual result is positive. This is a type 2 error or a false negative. It indicates a mistaken failure to reject the null hypothesis. Now, as a side note, we don't need to get too concerned with the term null hypothesis. This is just a scientific term representing the possibility that my hypothesis or my expectation cannot be demonstrated to be true. For example, if I expect that my burrito mess can no longer be classified as edible food, then the null hypothesis is that it's perfectly safe and edible. If I expect that human activities are causing rising global temperatures, then the null hypothesis is that human activities are not influencing global temperatures, and so on. Now, in reference to our earlier example of suspicious leftovers, I'm similarly facing a binary outcome condition. A type 1 error in this case means that I think the burrito is spoiled when it's actually still edible. While I'm avoiding food poisoning either way, it also means I've unnecessarily sacrificed the opportunity for a fulfilling meal. A type 2 error occurs when I think the burrito is safe, but it actually isn't. Your Imagine will do a better job than I will of visualizing the brutal horrors that await you under these conditions. Now, technically, our hypothesis and our null hypothesis could be assigned in either direction. For example, that the burrito is safe or that the burrito is spoiled. We could assign either of these as our hypothesis, and the other would be the null hypothesis. But in most scenarios, we can simply observe the question that we're asking. If my burrito looks fresh, then there's no question. There's no hypothesis, no prediction, no test. I simply assume that it's safe. But when it's a bit funky smelling, we're asking the question, is it spoiled? So it makes the most sense in this scenario for my hypothesis to be that the burrito is spoiled, and then the null hypothesis becomes the burrito is still edible. We can think of similar examples in medical diagnostics. Am I free of disease is not typically how we apply diagnostic tests. Instead, we will typically ask, for example, do I have hypertension? And we will apply a diagnostic test for hypertension, like a blood pressure cuff. And so this becomes our hypothesis. I have hypertension. With the null hypothesis, or the default state, being I do not have hypertension. Again, you can set up your hypotheses in either direction, but in most scenarios, one will make more sense than the other. Now, this is all nice and academic, but type 1 and type 2 errors have a lot of influence on our everyday decision making. And this is because when we avoid one type of error or the other, whether due to conscious preference, unconscious fear, or situationally dependent logical prudence, we will increase the likelihood of creating the other error type. And it's easy to make sense of this with our burrito example. If I err towards judging that my leftover burrito is spoiled, for example by playing it safe, I become more likely to avoid type 2 errors. But simultaneously, I become more likely to commit type 1 errors. That is, I'm less likely to eat a spoiled burrito by mistake, but more likely to throw away a perfectly safe one, and vice versa. Imagine, for example, that I'm evaluating 20 boxes of week-old leftovers. Let's say I'm evaluating the leftovers both by appearance, for visible mold growth, we'll call this the slime quotient, and I'm also evaluating by smell, we'll call this the stankiness factor. And I have some internal threshold, whether consciously determined or qualitative and instinctive, and below this threshold, I'll eat the burrito, and above it, I will deem it unsafe and I'll throw it away. Now, if my threshold is lax, I'll occasionally eat the wrong burrito and get sick. This is a type 2 error, while I may still experience a few type 1 errors as well. Now, alternatively, I can choose to use a more strict threshold, zealously throwing away any burrito with even a hint of stank in order to avoid type 2 errors. When I do this, I will inevitably create more type 1 errors. Now, the interesting thing to note here, and this is often the case, we know when we've committed a type 2 error. Type 2 errors are potentially dangerous or even lethal, but it's very obvious when we've made one, even if only in retrospect when it's far too late to correct it. Type 1 errors are a bit more ambiguous. Committing a type 1 error is inconvenient, but rarely lethal. However, their insidiousness lies in the fact that we don't know when we've made them. Unless we're following up on all positive results with a more precise test that has a lower false positive rate, we'll never know which, or how many, burritos we've discarded that were actually safe to eat. Type 1 errors are unknown unknowns, and these errors can compound over time to create stupendously suboptimal long-term behaviors. Now, while a better diagnostic test will typically decrease the overall error rate, the trade-off between type 1 and type 2 errors will persist. In designing our systems or honing our thought processes, we're always asking the question, whether consciously or subconsciously, we're asking, do I want to preferentially avoid type 1 errors or avoid type 2 errors? And importantly, this is an either-or question, not a yes-both question. Recognizing and becoming aware of this trade-off is crucial to understanding ourselves and making better decisions, especially when that decision is made subconsciously. But unfortunately, things can get even more complicated. Let's talk about the base rate fallacy and the false negative paradox. First, we'll consider as an example the rates of hospitalization due to COVID in a population consisting of both vaccinated and unvaccinated individuals. I might want to know the answer to the question, does vaccination reduce the hospitalization rate? Now, if the hospital has a greater number of patients who are vaccinated compared to those who are unvaccinated, I might conclude that vaccination doesn't reduce hospitalization. However, without knowing the numbers of vaccinated versus unvaccinated individuals in the population, this conclusion is inaccurate. For example, in a population in which vaccinated individuals vastly outnumber unvaccinated ones, it could very well be true that vaccination reduces hospitalization, and simultaneously true that more vaccinated individuals are hospitalized than unvaccinated individuals. A study on COVID deaths and hospitalizations in Washington state demonstrated just that. In populations with high vaccination rates, for example, over 85% vaccination rate in 65-plus-year-olds, a greater number of vaccinated compared to unvaccinated individuals were hospitalized with COVID, and yet the likelihood of being hospitalized was still lower if one was vaccinated. Drawing conclusions about the effectiveness of vaccination against hospitalization based solely on the number of cases without considering population sizes, this is an example of the base rate fallacy, and it can easily cause us to make poor or uninformed decisions in day-to-day life as well. For example, maybe I'm trying an untested dietary supplement based on positive anecdotal evidence from a small number of people, but I might be ignoring a much greater population of people who tried it but didn't experience positive results. Or maybe I have a friend of a friend who makes $10,000 a month selling digital goods on Amazon, but that doesn't necessarily mean much if the majority of Amazon sellers make far less. Or I might hear about a catastrophic plane crash in the news and then decide that flying is unsafe. However, rates of accidents and death by automobile significantly exceed those by airplane. And the base rate fallacy can be even further complicated when we consider false positives or type 1 errors. The false positive paradox can lead us to incorrect conclusions in scenarios where the number of false positive results exceeds the number of true positive results. This can easily occur in any situation in which the likelihood of a true positive is very low, or in instances in which our test is not very specific. In other words, the rate of false positives is high. For example, let's say we're screening for a disease in which 40% of the population is expected to be infected, and the test has a 5% false positive rate. In other words, if I screen 1,000 people, I would expect 400 true positive results, or in other words, successfully detecting infection in an infected person. Of the remaining 600 results, I would expect 5% false positives, or 30 results. This means that the total pool of positive results is 430, 400 true positives plus 30 false positives. So of those 430 positive results, 93% of them are true positives. So any given positive result is likely to indicate someone who's actually sick. But let's say the rate of infection were far lower, at 2% of the population. Now when I screen 1,000 people, I'll expect only 20 true positive results. But with a 5% false positive rate on the remaining 980 results, I'll expect 49 false positive results. This means that I'll have a total of 69 positive results, of which 49 are false. In other words, only 29% of positive results are indicative of an individual who's actually sick. In other words, even having an understanding of how likely our test is to produce false positive or false negative results is not sufficient to estimate the absolute numbers of those results unless we also know something about the population we're testing. For example, when I'm examining my ambiguous restaurant leftovers, I'd need to know both how accurate my stankiness test is and roughly how often my leftovers are truly spoiled. Needless to say, we typically do not have this level of detailed information when it comes to everyday decision making. And so it becomes even more critical to be aware of the potential pitfalls in our ad hoc analyses. But even if we can ignore false positives and false negatives, and we shouldn't, but even if we do, there are even more issues that will cause problems for us. Let's talk about type 3 and type 4 errors. Now, a type 3 error can be described as correctly rejecting the null hypothesis for the wrong reason. Now, unlike type 1 and type 2 errors, errors of type 3 aren't so much about differences between the prediction and reality, but rather about incorrect use of the correct conclusions. And type 4 errors describe a mistake in which an experiment doesn't truly test the intended hypothesis, leading to an invalid conclusion. Compared to a type 3 error, it's not my interpretation of the results that's incorrect, but rather the study design itself. Now, sometimes type 3 errors are a simple case of confusing correlation with causation. This is another topic I'll surely cover in more detail another time. For example, if I see an association between drowning deaths and ice cream consumption, I may warn people not to swim after eating. However, the actual cause of increased drowning may be warmer outdoor temperatures that promotes greater rates of swimming and concurrently greater rates of ice cream consumption. Or in our burrito example, I might conclude that surgically removing bits of mold from the top of the leftovers, effectively reducing the slime quotient, will make the burrito edible. I've correctly concluded that the burrito was inedible, but my determination as to why it's inedible, seeing the mold on the surface, ignores other causes, such as unseen mold or bacterial toxins permeating the depths of the leftovers, which my topical surgery would fail to address. But type 3 errors can also be caused by willful ignorance of the implications of a test result. For example, if I manage a company but I struggle with employee disengagement and low productivity, I may correctly conclude that long hours and low pay are likely the cause. However, if addressing this issue is too costly, I may instead decide to offer free lunches every Friday. In this case, my observations suggest that my hypothesis is true, my employees are disgruntled, and I've correctly identified the cause, poor working conditions or compensation. But I've chosen a course of action that fails to address the cause of the problem. We may willingly commit type 3 errors when we sufficiently understand a system to determine appropriate corrective actions, but choose not to do so anyways because it's costly, time-consuming, inconvenient, or unpleasant. Now, when it comes to type 4 errors, or essentially bad experiment design, these types of errors can be a major cause of poor personal decision-making because the world we live in is very complex. Designing and implementing a test to accurately predict an outcome can be time-consuming or expensive, or it can require substantial expertise, resources which are often unavailable or impractical to utilize when solving everyday problems. For example, I could try a new dietary supplement hoping it will help me control anxiety or lose weight, but I might fail to see results solely because I didn't take it long enough, or I used the wrong dosage, or because I was taking another supplement or drug at the same time, which interfered with its activity. Under more favorable test conditions, the supplement may have actually had a positive impact. Or I may hear overwhelmingly positive reviews about an online course for learning a new skill, but I may still fail to get value from that course because I got distracted while watching the videos at 2 times speed and while simultaneously doing other household chores in order to be efficient. Or maybe I decide that doing my own car repairs is feasible based on a YouTube video that I watched, but I don't have all the specialized tools needed to perform the repair myself. I try to perform the repairs using conventional tools, but fail to successfully repair my vehicle. When we fail to understand a system sufficiently, and instead we make guesses, assumptions, or substitutions to a method that we want to try, we're risking a type 4 error. And these errors are misleading because they can cause us to come to false conclusions, when in reality we simply haven't performed the test appropriately. Now, I should mention that type 3 and type 4 errors are not widely accepted concepts within statistics. However, the ideas behind them are still useful in generating awareness for the mistakes that we can and often do make when testing hypotheses, interpreting data, or drawing conclusions, both professionally and in everyday life. Now, we humans pride ourselves on being rational creatures, weighing evidence and making sound decisions. But reality rarely gives us clean data, clear instructions, or enough time to run a double-blind trial in the short span between yoga class and dinner. Whether we're scrutinizing our aged leftovers, evaluating nebulous health advice, or deciding which projects to pursue, we're constantly navigating uncertainty. And while we can't completely eliminate errors, we can learn to recognize the kinds of traps that we fall into. Reacting too quickly, hesitating too long, solving the wrong problem, or giving up on something just because our first attempt failed. The goal is not to eliminate error, but to be aware of the potential errors that our circumstances subject us to making, to recognize our blind spots and evaluate as accurately as possible when it's worth it to play it safe or to take a risk. when we should have confidence in our analysis of the situation, or when a healthy doubt is the best answer.